Welcome back after the break. I hope you're refreshed and that we can go through the last session before we break for the day. Right. We would like to go on, if we look at the concept map, I would like to go on with our equilibrium, where we will look at acids and bases and apply Le Chatelier's principle to acids and bases. When we apply it to acids and bases, I would like us to look at the auto-ionization of water again. And here we know that water likes to be in the molecule or the molecular form, and only a little of the water will go over into the hydronium ions and hydroxide ions. So the question here is, if we have water which is a neutral substance, what will happen, according to Le Chatelier, if we add some acid to the water? Now we know that an acid has got a lot of hydronium ions in solution, and that's what will let us know that we're working with an acid. When we have the water and we've added the acid, if we use our Schreef methodology that we've learned earlier, the stress here is there will be an increase in our hydronium ion concentration, and according to Le Chatelier, the system will try to decrease this hydronium ion concentration. Now, when the system will try to decrease the hydronium ion concentration, it will obviously now favor our reverse reaction. So our reverse reaction will be favored, which means that we will now actually decrease in this process of favoring the reverse reaction. We will decrease the hydroxide ion concentration, and a decrease in our hydroxide ion concentration actually means that our pH will decrease. And a decrease in pH actually means more between 7, from 7 to 0. So what will happen if a base is added to the closed system? We know that a base, we can see that something is a base because of the presence of more hydroxide ions in solution. So our stress or our disturbance here will be that there will suddenly be more hydroxide ions in the solution. According to Le Chatelier, if we have a high concentration of hydroxide ions in the solution, it will basically mean that the reverse reaction will be favored. And if the reverse reaction will be favored, it will be done because the system will want to try to decrease the OH minus concentration. And when it does that, favoring the reverse reaction, there will actually be a decrease in our hydronium ion concentration, and a decrease in hydronium ion concentration means that the pH will increase. So the pH will then be bigger than 7. What will happen to the pH when ethanoic acid is added to water? Now, what we need to know is ethanoic acid is vinegar. Vinegar is not a harmful acid. So vinegar is also a very weak acid. And we know, according to terminology, a weak acid is an acid that will not completely ionize. So if we go look at what happens to water, this is our water, auto-ionization of water. Water will break up into hydrogen ions and hydroxide ions. If we're going to add vinegar to the system at equilibrium, we will obviously increase the hydronium ion concentration. So let's unpack. What is the disturbance? We've added vinegar to water, and this is now just to water. So when the vinegar is added to water, there will be an increase in the hydronium ion concentration. We could have also said hydronium ion concentration instead of protons. And the response here is that the system will try to decrease the hydronium ions in the solution. By doing that, our reverse reaction will be favored for both of our reactions here, and there will be a small a small decrease in my OH minus or my hydroxide ion concentration, which then means that little bit of hydronium ion concentration there will actually let our pH decrease slightly. A decrease or a slight decrease in pH means that the pH will be smaller than 7. When we're comparing strong and weak acids, if we think we must know for the exam, we must know hydrochloric acid is a strong acid, and a strong acid, even if it's diluted, even if there's a few number of moles in the volume or a lot of moles in the volume, it's still a strong acid because it completely ionizes. There's then a high concentration of ions in solution. And that high concentration of ions in solution means that the product is more than the reactant, meaning that the Ka value is very high. And when the Ka value is very high, we know we look in terms of a pH very close to 0, between 0 and 2. And when there's a lot of ions in solution, such a solution can conduct electricity very well. So high Ka value leads to good conduction or very good conduction of electricity, and obviously a very high reaction rate. When we look at ethanoic acid, which is now a weak acid can also be concentrated or dilute. When it's concentrated, there's a large number of moles in the volume, and when it's diluted, there's a low number of moles in the same volume. So when we look at ethanoic acid, it's got a very low concentration of ions, and specifically the hydronium ions and whatever the anion is, and it leads to a very low Ka value, and the pH is then very close to 7 on our pH scale. And it does conduct electricity poorly because there's only a few ions in solution, and the reaction for such a weak acid will be a low rate of reaction. When we look at sodium hydroxide is a strong alkali, or we can say an alkali because sodium hydroxide is soluble in water, but other people will just say it's a strong base. And even if it's dilute, it's still a strong base because it completely dissociates. Because it completely dissociates, there's a very high concentration of ions in solution. Again, the forward reaction will be favored, meaning the equilibrium will lie more to the right. There will be more products than reactants, making our Kb value very high. And if you have a high Kb value, it basically means you will have a base very close to a pH of 14. Because the Kb value is so high and there's such a high concentration of ions, the strong base can conduct electricity well, and because of the high concentration of ions, there's more collisions per second, more effective collisions per unit time, and then the rate of your reaction is higher. When we look at ammonia, which is a weak base, weak alkali, soluble base in water, even if it's concentrated, it's got a low ion concentration, meaning it will conduct electricity poorly. Because of the few ions in solution, there will be less collisions, there will be less effective collisions per unit time, and a lower rate of reaction. And this ions, the low ion concentration also leads to a low Kb value, meaning that the pH is closer to 7 on its way to 14, but a weak base will be more or less there. So this brings us to the end of our acids and bases, but I just want to summarize quickly. Ionization constant of water, we spoke about it at length. This is also a formula on our formula sheet. Your pH is done by the minus log is equal to minus log times hydronium ion concentration. We spoke about pH plus pOH, that's equal to 14. Strong acids ionize completely and it's got a high Ka value. Strong bases dissociate completely and it's got a high Kb value. And this brings us to the end of today's session. I hope you've learned something. Go well.